Office hours today, I'm cutting them 15 minutes short. I need to be somewhere. So they're going to be just till 3:15. So it'll be right after class until 3:15. And I decided I would splurge. And rather than have it in the lab, which is not that interesting, I'd have it in the cafe and have myself a latte. So I'll be there from 2:30 to 3:15, whether anyone's there or not. Review Lab 1 feedback before you turn in Lab 2. So the Lab 1 feedback, the easiest way is just to go to GitHub and click on the Lab 1 feedback branch and look at the last commit, and then you'll just see all of my notes. But I'll just give you an example. So let's say you have some code that you're submitting that says, I don't know, calls bootmap region or something. Okay, great. It's good looking code. When you are submitting your code, it's as if we've got some shared repository of some project you're working on, right? You're working on an OS, and this is your contribution to the OS. You don't want, as part of your contribution, a comment that says your code here, right? Because someone coming along later is going, what? Right? For you, it was handy. Someone put a little pointer in the code that said, in the operating system said, hey, here are some good places for you to put in code. I'll even give you some hints, too, on how to do it. When you're done, there shouldn't be your code here, and there also shouldn't be hints, So, does that make sense? Okay.
Can we leave in the requirements?
Requirements is great because the requirements is a good documentation of what's there. So that's fabulous. So yeah, just do that before you turn in Lab 2. So we were talking about paging, and we have a fair amount to continue about paging. On the x86 in particular, we're using this 2-level page table where x86 calls the first level a page directory and the second level a page table. This could just as easily have been called the first level page table and the second level page table. We use CR3, and that contains a reference, a pointer to the page table in physical memory. Right? It's a physical address. So very few places in the CPU are we dealing with physical addresses. But the page table pointer is one of them. Because if not, where would it go look to convert the virtual address to a physical address, right? In some other page table, which it has some other virtual address for, right? So we need some way to stop this infinite recursion, so we stop at 1. So this is a physical address, and the physical address is broken down into 10, 10, and 12, right? 10 bits for the page directory index, 10 bits for the page table index, and the remaining 12 bits are the offset within the associated physical page table. Page tables have to start on what bounds? In physical memory, the physical page frames, what sort of alignment do they have, Giselle?
They have to be aligned on a page.
Yeah, on a page, there's a 4K boundary. And the reason for that is we have this page table number here, right, which is basically takes us to that 4K boundary. And then we add in the offset. These 12 bits are the same as these 12 bits. These 10 and these 10 happen to be the same size as these 20, but as we talked about on Monday, they could have been different size. We could have had more physical than virtual or virtual than physical. Happens to be the same. And each of these tables, as well as our physical page number, has flags as well. Like, can the kernel, can user mode read and write it? Can it be written? Is there even anything there? Right? And the CPU will check the flags in both places. So if you try and issue a write to this physical address that's taking us through here, and you're in user mode, it's going to check to make sure the write flag is set here, and the user mode is set here, and that the write flag is set here, and the user mode is set here.
So what does PPN stand for again?
The physical page number. Okay, so let me just throw that in here. It's a good question. And the fact that this is a physical page number in the page table is not surprising, right? Because we're trying to get our physical frame, our physical address. This is a physical page number as well, because, again, we're trying to implement virtual to physical mappings. And so we need to have some stability. So CR3 is physical, and these are physical too. Aaron?
Are page directories constant from process to process?
So as far as the hardware is concerned, it will just always look at CR3. Does that make sense? So what we choose to do with that is a different story. And the short answer is yes. Every process is going to have a different page table. And so part of switching between processes, like switching the stack, switching the instruction pointer, we also need to switch the CR3. Sarah?
I know in JAWS for the page directory we set the permissions just to be pretty permissive. Is there a reason that there's both permissions on the page directory and page table? Is it like to make it fail faster? Or?
So I think you're talking about the struct page info thing, that pages? Is that right?
Like the flags, the permission like user versus kernel, like read write, they're on both the page directory and page table.
So they're in both of them.
Yeah.
What we do so here's the problem. Let's say we're going to check both of them.
Yeah.
Okay? Let's say this one is user mode.
Yeah.
This page on this page table is user mode, and everything else is kernel only. Okay? It's a weird virtual address space, but let's just say that's the case. If we say this is kernel only, we can't ever get to the user one. And so therefore, if we make it wide open here, we say kernel and write here in the page directory, then we just specify exactly what we want here.
I guess my question is why we have them in the page directory.
Yeah, that's a question. It's a good one. Yeah, you could certainly do without having the page directory. So actually, this would allow us to, for instance, if we wanted, I guess, have a large range of addresses where we got a different error, let's say in user mode and kernel mode. So we could have a large array of addresses where we said the user can't write. And then if the user tried to write or read, right, they'd get an error, and the error would be that we have the wrong, that we're using user mode instead. That could be differentiated from whether those actual page tables were there or not. So we could get a different error on our page fault, giving us a different error message. But yeah, in general, I can't see cases where you would often use this. Brad?
So when you say that every process has their own page table, does that term encompass both the page directory?
Yes. I mean the whole page,
Okay.
the whole structure. Yep. And there is some sharing that one could do, and we'll talk about that a little bit later today. So to look in more detail at the page table, so page table entry and page directory entry are astonishingly similar looking, right? We have how many bits for the physical page number? 20, right? And then we've got a bunch of bits, and the ones we really care about are the user, the write, and the present. Many of these you can actually I think it's the AVL is available. So it's 3 bits that you can use for your own nefarious purposes. So we'll come up with some ideas on what to do with that. But you can just sort of keep track of some things in the page table. And the other ones we don't care about that much. Dirty's interesting. So if you use an address to write to it, right? The CPU knows when you're writing, then it will set the dirty bit on the associated page table and page directory. It'll never clear it. It's up to you to do that. But you can at least know, since the last time this was cleared, someone has written to some of that 4K within this page table. Right? Access tells you if someone's read from it. Cache disabled says don't do any caching of this. Right? Normally there's an L1 cache or an L2 cache between the CPU and the main memory to speed stuff up. And this says don't use that cache. Why would we not want to use the cache? Nandika, can you think of any case where you wouldn't want to use the cache?
There's some levels of the cache where like not all
Okay, so we could have non-shared areas of the address space, possibly. That could be.
That then, if you wanted to like have somebody like write or somebody to send memory.
Let me give you an example. Can you think of a case where I want to go out to the bus and read from a memory location and just loop through reading, let's say, and I expect it to change over time, and there's no multiprocessor running, right? So there's just a single processor, and yet I expect it to change over time. Giselle?
So like memory mapped IO.
Memory mapped I/O is the best example of this, and yeah, I was burned hard by this on the one time I was writing device drivers, because if you don't turn off caching for that, you're trying to read, you're expecting the hardware to change a value at an address, but the cache is not even bothering to go back and look. It got it once, it's not going to change. So often we turn this off, or turn the cache, we disable the cache for memory mapped I/O. Okay. Questions? Yeah.
So, what would be an example of this external hardware that like has to do with memory mapped I/O? Does every piece of external hardware?
Lots of hardware has memory mapped I/O in the sense that we reserve it a little bit of the address space, right? So we might have a portion of the address space for the Ethernet controller. Okay? And it might have not a huge address space, but it might have tens or hundreds of bytes of address space. And so one of the things there might be is a bit that says a packet just came in. Or not a packet just came in, I have a packet. Okay? And so you might just keep going until that value is 1. Okay?
And you don't want the cache to...
The way the cache works, right, the first time you try and access it, it'll go find out what is actually the other end of that, you know, which as far as it's concerned is memory, but it turns out is the device.
Yeah.
It gets back a 0, and then the cache holds onto the 0 and just keeps feeding that back to you. So, in fact, you have different caching in a lot of different ways, right? If you're not careful, right, you're in C, and you say while, I don't know, present equals 0. And we say char star present equals OX 10532, right? Whatever our space is in the memory mapped I/O. So while present is equal 0, you know, do nothing. Otherwise, now read our packet in some way. Well, our optimizer, sorry, not while present, while star present, because we want to dereference our pointer. So we assume there's a character at location 10532 that's hooked up to our Ethernet controller, and if there's no packet there, there's going to be a 0, and if there is packet, it's going to be a 1. So we're going to just loop through while star present equals 0. First problem is the compiler. The compiler wants to be our friend, speed stuff up, right? And so what happens here? As far as it's concerned, it's either an infinite loop or not, depending on the first call to present. But it certainly doesn't have to keep rereading it, because it won't change, right? So, so you have to first keep the C compiler to keep trying to read from there. The solution to that, Julius? Do you know in C how you tell it that a value may change out from under it? Exactly, volatile. So you throw in, and then I always will be careful to look and see where my volatile goes. But I think in here, it goes here, that it's a volatile char. It's a pointer to a volatile char. So it's a pointer, as opposed to, yeah, that is correct. So now all of a sudden the C compiler will cooperate, but then the cache is going to start telling you, oh, the first time it was 0, so I'll just keep feeding it back 0, but I'll do it very quickly. Okay. So that's why you need to turn to cache disable.
Okay, that makes sense.
Okay. Oh, no. All right, so the way that segmentation and paging interact with one another is first we segment, and then we page the result. So we go through the segment translation. That gives us a linear address. So the way the x86 documentation describes it as logical address, linear address, physical address. In some ways, these are really both virtual addresses, right? Because they're not the true final address. We're not doing much with this in either of our operating systems. We're going to be setting these so that the base is 0. Questions on this? So the good news is you guys are all doing the lab is you become intimately familiar with the page table directory and the page table entries, right? All right. So what happens if you try and read or write to an address, a virtual address, for which the PTEP bit is not set? Dave.
PTEP bit being
In so PTEP is the present bit, which is right here. Right? That's saying whether this page table entry or page directory entry is actually present.
So wouldn't that cause a page fault?
Yeah, cause a page fault. Or if you're trying to write and it's not writable, or if you're the user and you're trying to write that something's kernel only, in all those cases you get a page fault. What does the kernel do in that case? I mean, it depends. It does what it wants to do. So it could kill the process. That would normally be if this is a user mode, right? This is, it could go ahead and modify the PTE and then restart the instruction. So resume the process, restarting the thing that was causing the read or the write. So for example, virtual memory that we'll be talking about some more today and more in a later lecture. We haven't actually put the page into memory yet, right? We just marked that, kept the page table entry to say that it's not present, and then when someone actually tries to access it, we will go ahead and load it. And then once we're finally done loading it, we'll go update the page table entry and then return back to the user process and restart. Okay. So, does it make sense? This restarting idea? Do we have to use virtual memory in the kernel? Could we use real physical addresses? Yes and no. So hardware often makes it difficult to turn off paging. Like, give me an example, Fabio, of an architecture that makes it hard to turn off paging once you've turned it on. Anyone? x86, right? Once you leave real mode, there's no going back unless you reset the processor or triple fault. And so it's pretty hard to go back. So therefore, you're going to be using the virtual memory hardware anyway.
Can't you turn off paging by making an identity mapping?
Is that turning off paging, or is that just making an identity? I mean,
That accomplishes the goal of letting the kernel interact with physical memory.
yeah, you could certainly do that. You can set up a one-to-one mapping, given that our virtual and linear addresses are the same width as they are in x86. So one could do that. You'd often need to turn it off and on when you entered and exited a system call, right? If you could turn off the paging easily. And page tables allow us to avoid external memory fragmentation, right? Because the kernel is going to be doing a lot of allocating of memory and deallocating memory, right? As you open files and close files, create processes and destroy process, all of those are doing the equivalent of mallocs and frees. And that can get you into this problem where you have this external fragmentation. By doing it on page boundaries, we can allow us to have contiguous virtual memory referring to non-contiguous physical memory. Let's do my quick erasure. Oh, then I have to set other stuff up too. No, I just have to do that. All right. So, address spaces. The address spaces are confusing for two reasons. One reason they're confusing is it's just confusing. There are three reasons. The second reason it's confusing is you have different address spaces for different parts of the OS, right? You have the kernel, you have different user processes with different page tables, plus a boot page table, which makes things even more confusing. Plus, we get two operating systems going on that have different maps. That's confusing. Okay? So whenever I show you the address space, I will preface it with xv6 or JOS. And if I don't, ask, because it matters. So in xv6, right, we map everything from 800 on up for the kernel. And everything below here is for user space. And we're going to start our code here at 0. So the code is going to be here in the globals, and then our stack, and then our heap is going to grow down, kind of. So our stack will grow up, our heap will grow down. Questions on that?
In
Right.
JOS, is the BIOS at the where's the BIOS in JOS?
So also in JOS, the user stuff is at the bottom. And so therefore, it would not be convenient to have the BIOS mapped in there at the bottom.
No.
So physically it is, right? Physically, we got between 640 and 1 megabyte. xv6 maps let's see, our physical memory from 8, and in JOS, it's F, right? We're starting our physical memory at virtual address F, 000, whatever. Okay? So it'd be at the low Fs is where BIOS is. 640 plus the low Fs. All right, so looking at this in more detail, in the user side of things, our text, that is our code, is going to be read-write by the user. And we're going to have all these fitting in pages. And the data is read-write by the user. Why that code is writable? There was an argument we could make that it shouldn't be writable, but it is. We're going to have our stack here, and we're going to have one page of stack. If we wanted to have more pages of stack, that'd be fine. Where's the stack pointer actually going to initially point for a user-level program? David, at the top of this page or the bottom of this page? So my question is, I want to put a setting, right? I'm trying to initialize ESP. ESP. Where do I want it to point? That'd be great if stacks grew up. But on x86, stacks grow down, right? When you do a push, it decrements the stack pointer. So we'll have this go to here, right? And if we wanted more stack space, I mean, this isn't, in some sense, this isn't very convenient. We have this fixed stack size and we can't increase it, right? If we wanted to have more stack space, we'd have to allocate more stack ahead of time and then again move down, right?
Wait, so what does a program do if it, wait, so it only gets one page? You don't have any.
That's the way we have it right now, yes.
Would the compiler at compile time realize that the more stack space is being needed, so it would allocate more pages?
The compiler has no idea of how much stack space
So how does
is
the
needed.
program not to allocate more than one page of stack space?
With this setup, one can't. So xv6 is pretty limited. I will describe a mechanism we could use. So if we swap this around and put the stack up at the top, then after this page was done, we could go allocate another page. And then if that was done, we could go allocate another page. Now we'll talk in a little more detail later on today about how actually one would do that. Okay. And we're loading all this at what? 8100 whatever. So our code is up here. Our data, free memory, and we have device memory mapped at the very top. So we've got some memory map devices at the top, extended memory and so on. Fabio.
So, like, where does the user stuff get mapped to the physical memory? Because it seems like everything, only like the kernel has the lines mapped. So, what part of the physical memory would the user stuff map to?
Oh, so we basically the user, we're not going to map anything to IO space. And we're not going to map anything into our memory mapped 32-bit IO devices. So we're going to be mapping somewhere into the extended memory and base memory. So for instance, this one page of user stack might, I don't know, go to a page in here. Right? So that page is mapped twice, right? There are 2 virtual addresses you can use to get to that same page. One from up, because we're mapping all of physical space, and one from our user. But that's okay and necessary because we want to have different permissions. Right? So we have our own address space and our own page table. And those are kind of one and the same thing, right? If we don't have our own page table, then we must be sharing the address space with whatever page table, whoever has the same page table. So different page table. Do different page tables necessarily, Katie, mean different address spaces?
No, not necessarily.
Because?
Because things can be mapped multiple times.
So I've got an address space here. And I've got an address space here. No, I guess that's not really my question. My question is I've got a page table here. Page table 1, and when I'm talking about page table, I really mean the entire page directory and associated page table. And I got page table 2 here. Are these, and the page tables impose a mapping, right? They impose an address space. Do these necessarily, are they necessarily different address spaces? Or could they be the same? How would they be the same?
Well, one example is like page table 1 could belong to a user, and page table 2 could be somewhere in the kernel and they can map to the same physical space like you were talking about.
Yeah, but the entire address space. So I'm talking about the entire address space. So address space 1 has some mappings to physical memory, right? And then page table 2 imposes an address space. And that imposes some mappings to physical memory. Do these mappings have to be different?
Yeah, no.
They don't have, because we could just have a copy, right? So we could have officially separate page tables, but if they have the same contents, then we have the same address spaces.
Would that be like maybe right after you fork?
Exactly. Right after you fork, we would have a duplicate. Yep. I'll back up a second. As an optimization, right after we fork, we can have a duplicate. Normally what happens is we actually, the slow way to do it, is go through and for every user page, duplicate the page, meaning we'll have separate page table entries here. They'll be similar, but they'll be pointing at different physical pages. An optimization would be share the same physical page with 2 different pointers.
So would you
Question,
have
right?
to have a flag that was different in page table 2 that would say like copy on write or something?
You would want to have, and this is getting ahead of ourselves, but you would want to have a copy on write flag in both page tables, because if either one of them modifies it, you want to make a duplicate. We will talk more about that. All right. So the user address in XV6, 0 to 2 gig. It's very simple. It's all wide open. The kernel space is already mapped correctly. And so therefore, when we switch to handle a system call, we wouldn't have to change page tables, right? We could keep the same user page table. Right? And we do actually keep the same user page table while we're handling a system call. So that's nice because if we're doing, let's say, a write or a read, we need to access user memory, and we have exactly the mapping we need to get there. But we can also access kernel stuff because all that mapping's there too. The kernel's mapped at the same place for all processes, right? Starting at 8.1 or 8.0.1.0, whatever. They could be everywhere all different. We could have user process 1 have a mapping where the kernel is here, and process 2 has one that's here, and process 3 somewhere else, and that could work, but it wouldn't be fun. So we have them at the same place. Easy to read and write. We just use a virtual address because we are still using the user mapping. And it's easy to read and write physical memory because we have a offset that takes us to physical memory. Right? Questions? All right, so actually the stack isn't right by the data, as we showed in the previous slide. There's the stack, and then there's a guard page. So we have our global variables. We have the stack here. We initialize it up the top here. We only go to 1, k. And then ideally, we would blow up. If we don't have a guard page here, the non-ideal case is we start bashing global data. Do you see how that would happen? Which is not the preferred solution. So we can put a guard page in here, and the guard page basically says there's nothing here. So if the processor tries to read and write to data here, what will we get? Drew? We'll get a page fault. And we will look and we'll say, what address was this? Because that's important information. What address caused the page fault? Because otherwise you can't do much. And we'll say, oh, it's in here. Oh, wait, that's our guard page. Uh-oh. What are we going to do? Report back to the user process, hey, you exceeded your stack space? Stack, we could create. Yeah, so we'll get a Stack Overflow, exactly. So, and we'll exit the user process. Okay. Ashley.
The guard page, like, if it reaches the boundary for the data page, like, why can't you just make it?
What are the permissions for the stack? Right, is the present bit going to be set? Yeah. Yes, so P or is the write bit going to be set? Yes, and can the user write to it? Yes, because it's our user, right? It's our user code that's writing to its own stack, so that's okay. And what about the data? Same. So therefore, we're not going to get any exception, right? The kernel's not going to get any exception. And all that'll happen is if we do pushes, let's say, push, 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 there's no guard page there. We just keep pushing. And the permissions are identical. And yes, it'll cross a page boundary, but as we would like to have happen, there's nothing special that happens when you cross page boundaries, right? As long it has to go through a different page table entry, but it'll treat it all the same. And if the permissions are the same, that's what'll happen. Does that make sense? We still have a potential problem here. Can you give me an example in C where we might have a stack? We might jump into the data here.
You could have an array on your stack that's like 8 megabytes.
So you have a local variable in a function that's declared to be really big. Okay? 8 megabytes seems like overkill because this is only 4K big. So let's do 20K. Okay, so you have a 20K array. When you have a 20K array declared locally, what does the compiler do? It just subtracts 20K from the stack pointer down into here, right? And then all of a sudden, and it doesn't do any writing. Right? C doesn't say that local variables get initialized to 0, so no one's going to be initializing those to 0. So until you actually use that array or read and write to it, nothing's happening. And so therefore, you're all primed, because the stack pointer's here, to blow up. Make sense? Okay. So we start the first process. The first process in XV6 is different from the other processes. The other processes get created... Gary, how? Sorry. Gary?
No.
Gary. All right. Gary, so how do we create processes in XV6? Sorry. Or in Unix? But how do we create so what system call creates a process? Nope, there's a nice one like that in Windows 32, and it's called create process. Anyone to help out? Andika? Fork. So fork says, given a process, duplicate it, right? So we have to have a special way to create the first process, because we can't fork it because we don't have a process to start from. So this is the base case, in some sense, of our recursion. So UserInit is going to do that. This initializes the user process, the very first process. And the first thing it does is set up the kernel virtual mapping. And then it's going to initialize the user virtual mapping. So the kernel virtual mapping is the part above 8, and the user is below. So let's look at that. So set up KVM. What it's going to do is allocate a page directory, right? Page size big, set it to 0. You've done this before, you know how that works. Make sure we're not, I don't know why we would have this. We'll have to look at that in a moment, or maybe we don't care about that right now. And then we basically do 4 mappings, okay? So it's kind of nice because we just have the mappings in an array. I guess you could do that in Lab 2 if you wanted. So it's just where we're mapping from and mapping to. So devices in one case, that's up at the top. The kernel data in memory. The kernel code and the read-only data. And then the I/O space. So all 4 of those for the kernel. The user is not going to be using that directly because it's all, none of it has the U bit set. Okay? But this will just ensure that this will ensure that the first user process has this mapping, and as we then duplicate the page directory, that all subsequent processes have this mapping. And then UserInit initializes the mapping for the user space. And it pulls a binary that was compiled in with the kernel image. So there's a very small binary we'll see in a moment, which is the init process. And so it just copies that code in. It's not very big. So, in fact, it fits in one page. So we're going to go ahead and allocate that page, set it to 0, map for our page directory from 0 to the page size, so that is the first page, the bottommost page, to this newly allocated physical page, and then copy the data from our kernel, this less than a page size of data, this small amount of code in there. So when we're done here, now we have one page mapped.
So the 0 is for the 0th virtual address.
The 0th virtual address, right. So we're at the very bottom of the address space. And then we do a few things that I don't care about right now. The most important thing is, though, we load the CR3 register with our page directory, with our new page directory. Okay.
Can you clarify V2P? Like, I looked at the definitions for it, and it was taking the virtual address and subtracting it by recurrent base is, but I wasn't totally.
Yeah, so V2B, V to P of A equals A minus kern base. And the reason for that is this mapping. Where's our mapping? Our mapping here. let's see, this is, I believe our mapping here from data to, so this maps from data to virtual to physical of data, that is kern-based less. And the amount we do is the top of physical memory.
Oh, that makes,
Okay, so this is basically just gives us our fixed offset for kernel virtual addresses from a kernel virtual address to physical memory. So you can go back and forth with a simple addition, not having to go through a page table, right, if you want to figure it out.
that makes sense. Okay.
The same as JOS, except that value is different, right? In JOS, it's F000 instead of 8000. So we set the CR3. And then, yeah, I'm not going to actually show you this live. Let's just look at it here. So before the CR3, if we go into QEMU and do an info page, and first off, how do I do an info page in QEMU? How do I use the console in QEMU? Does anyone know? Aaron? Control A, yeah. Control AX quits, and Control AC takes you into the console. And what I also learned, if you're using screen, does anyone use screen? Doesn't matter then? Tmux, okay. So anyway. So here is our page table, or really our entire page directory, our two-level page table, as far as QEMU sees it. And this is not a standard part of QEMU. This is part of the QEMU, the handcrafted QEMU that we're using that they did at MIT, right, to add this. So it shows, for instance, the VPN range, 80000. How many bits is 80000? 5 hex digits, and each hex digit is 4 bits, because it's 2 to the 4th is 16. So therefore 5 times 4, which is 20 bits. All right? So this is the combination of the PDX, the page directory index, and the PTX, the page table index. So it shows a range to try, and it doesn't want to show one entry for every single page table entry because that'd be giant, right? So instead, it collapses things together. If you have a page table with a bunch of entries that are mapping to adjacent physical memory, it'll just say this range maps to this range. Right? If they weren't adjacent, it'd have to tell you every one. But if they are adjacent, it just tells you what they map to. And assuming that the bits are the same. Because then I can just report, here are the bits for this entire range. And these are all the physical pages, right? So this is, 200 hex odd physical pages mapped to from here. So note that the first entry is at 80000, right? Which kind of makes sense. That's where our kernel starts, our kernel address space. And this is before we called LCR3. So we did not load the page directory of our user process, of our first user process. So what page directory are we using? Ryan.
Yes. Can you repeat the question?
What page table are we using in XV6 before we've switched to the new user process page directory? Yeah, the kernel. Yep, so this is the kernel page directory, which doesn't have any user stuff mapped, which is what we expect. What's the difference between this one and this one? Mostly, the biggest difference is we have something mapped at 0. Okay? We have one entry in the page table for page table index 0 and page directory index 0, which is just 0. And it happens to be physical page DFBD. Why DFBD? That's the first one in the free list. Okay? So our user process gets one page to run. And in fact, if we go back, What are we going to set the... No, I don't care about that. Okay. So the first process, you might want to be aware that a lot of the stuff between JOS and XV6 is similar, because the type of things you have to do is similar. So for instance, we need to map pages. So if you're working on JOS and you need to map pages, a good place to go for hints is XV6, because you have to do the same sort of thing. So always consider looking to XV6 for your labs to figure out what to do, and sometimes that might be helpful vice versa. Like walk page dir, it happens to have such a thing, which surprisingly has the same parameters and the same return result. So handy. Okay. But basically, this is exactly like the lab. We're just walking through the page directory to figure out what the page table entry is, and then setting it appropriately for an entire range. In our case, we just did it for one page. And walk page dir, I'm guessing since Lab 2 is due tomorrow, most of you already written a walk page dir. But if not, good for you, because you only have one day to do it. So now you know. Okay. Questions on this? All right, let's start a second. I wanted to provide a summary of the difference in segmentation and paging, because sometimes that can be confusing. So for paging, does a programmer need to be aware? Let's just run through these. So Ryan, you answered. Now let's just do them in unison. Need the programmer be aware the technique is being used for segmentation?
Yes.
Yes. Paging? No. How many linear address spaces are there in segmentation?
1.
Why 1?
Oh, 4. 1 for each segment.
Yeah, it's the number of segments. Every segment has its own, which 4 in the case we were talking about. Everyone has its own linear address, right? Because we get to map it with an offset and a limit to where we need to in physical memory, or at least in linear address, yes?
So the 4 segments correspond to like code the data. Is that what that's included by the 4 segments?
Yeah, code segment, data segment,
Okay.
stack segment, extra segment. And in paging, how many? Well, that's an interesting question, actually. I guess I would say the number of, in some sense, it's the number of page tables. But that's not a good answer. I like as a better answer 1. Right? As far as the processor is concerned as it's running, there's 1, whatever the current page table is, and there's 1 address space, and that's it. Okay, so as far as the process is concerned, how many address spaces does it get? 1, okay, with paging. With segmentation, it gets 4, or however many segments we have. Can the total address space exceed the size of physical memory for segments? No. For paging? Yes. And you're going to have a homework that you do a little bit from now, where you have this giant array that won't fit in the memory allotted to it, and yet you're going to still be able to work with it. Can procedures and data be distinguished and separately protected?
Yes.
Very easily in segmentation, because there are different segments, you have different permissions and so on. Paging?
With effort.
Hmm?
With effort.
I think that's a good description of it, with effort. If you put them on separate pages, then you can set up separate segments. Separate protections. Tables whose size fluctuates become made easy. A good example of that, I mean, there are 2 things I'm thinking about. Like a stack is sort of like that. Its size fluctuates. Dynamically allocated memory, like the heap, often that gets bigger and bigger So are those easily supported with segmentation? I would say yes, and here's why. Well, I guess we'd have to move stuff around in memory possibly. But we can always extend the limit. Basically, the limit register allows us to make our address space larger and smaller, which is kind of appropriate for tables with size. So we can sort of set up a segment with a particular table at a particular size, and then as a table gets bigger, increase, or it gets smaller, decrease. We've still got to make sure there's physical memory for it, contiguous physical memory for it.
Yeah, that's kind of what I was going to ask.
Yeah.
What if you have another segment?
Yeah, it's right up against it. Yeah, then that's more of an issue. You'd have to actually move it in memory, perhaps. And in paging, it's sort of like one per process is easy. Just start at one part of the address space and start working. When you have more than one, it's a little more difficult. Okay? 2 is not so bad. Start at different ends of the address space and start working together and hope you don't meet in the middle. 3 gets to be a definite problem. Sharing of procedures. Can that work in segmentation? It can, because I could share, right, the same code segment possibly. And in paging, I could share pages, right? Just make sure my page table entries, that I have access to the same physical page frames from different user processes. Come on, yes.
Can you explain why the programmer needs to be aware of segmentation?
Because of the fact, and this is more true in lower level languages than higher level languages, okay? And maybe I should even say programmer versus compiler, okay? But someone needs to know that when you're dealing with, let's say, accesses to global data, that you're using the data segment, and that we're going to have a separate address space from when we're dealing with code, and so on. Okay? And this touches just a bit on the, like C, where we want to have a pointer to something in a data segment, like a global variable, or a pointer to something in a stack segment. And there, wow, to do that in segmented architectures is difficult, because now you've got to make sure your pointer includes the segment too, as opposed to just implicit. All right, 101 fun things to do with paging hardware. It's actually an exaggeration. We're not having 101 things. So performance. So demand S-break allocation. Does this sound familiar? Yes. So demand stack allocation. Having a single zero filled page that stands in for all the zeros in your address space. Copy on write fork. So making fork be faster so that you don't copy all of the physical pages associated with the user process. Demand paging. When you start running a program and you've got, I don't know, 100 megabytes of code, do you really need to load all 100 megabytes before you start running? Let's just load the main and get going. Right? So that idea there is load code on demand. Yeah.
People ever implement fork without copy on write paging?
Yes. So the original V6 did not do copy on write fork. So fork was quite expensive. But modern times, no. Everyone does. You can provide brand new features like memory map files. We'll talk about that. So this is a way to read and write to files. But rather than having system calls and procedures that you're doing, just use addresses. Right? So you kind of have what feels like, or what is, an address, a pointer into your file, and you can read and write to it. Shared memory between processes, virtual memory, allowing us to have a larger address space than we actually have physical pages associated. So sbreak allocates more memory. As v6 was working, sbreak, when you called sbreak, allocated more memory. Is malloc a system call? Malloc is not a system call. Malloc is a library routine along with free. Where does malloc get the memory to do its work? Sbreak, exactly. What if it runs out of memory? Call sbreak again and ask for more. Okay, that's how it works. Malloc could call sbreak to remove the size, right, to decrease it. But that's kind of hard because if you can imagine, malloc has allocated a lot of different stuff, and it's likely there's some stuff over the top, that its free space is not contiguous at the top. So the idea is to speed this up, instead of allocating the space at the sbreak, allocate it later. So this is kind of like reserving an airline flight. Okay? You reserve a flight, and they say, okay. When you actually go to fly, what sometimes happens? They're overbooked, and they say, oh, I'm sorry. I know you have this ticket. It even has a seat number on it. Yeah, but there's no space. That can happen in this lazy sbreak approach, right? You call sbreak, and you say, I want a bunch of memory, and it says, here you go. Okay? I'll give you an address. And then you go to use it. Oh, well, I mean, I can't actually allocate it. I'm sorry. So there are some disadvantages, right? So there, yeah, Aaron.
Is calloc a system call?
Calloc is a system call, yeah.
And it allocates the memory.
Oh, sorry. Calloc is not a system call. Calloc is a kernel procedure used for allocating memory within the kernel.
Okay, so it's kernel only.
Kernel only. That's why we say K.
And then the function is separate from malloc.
It functions similarly to malloc. Calloc guarantees it's going to allocate things of a particular, it'll round up to a page size, which I guess is not that different from malloc, but it operates similarly. But you're always getting a new page, and so you can't just be as blithe as you are in doing malloc of allocating things, because your internal fragmentation could be quite high. You wouldn't want to do calloc to allocate 10 bytes. Okay, so t-page fault is one of the few dozen exceptions. Just like a trap, it goes into the kernel in this controlled way. So it can switch from user mode to kernel mode. And it goes to a particular vector, usually in assembly, and then calls into a C routine. The hardware makes sure we have all the information we need to actually handle the fault. That is, most importantly, the virtual address. Second, what was the violation? Was it a read-write violation? Was it a user kernel violation? Was it not present at all? And where were we executing? And what was the current permission levels? How could the current permission levels be anything other than 3?
Maybe we made a mistake in the kernel?
Yeah, so the kernel shouldn't get page fault exception, but it might if we wrote something wrong. And so that's a case where we get a page fault exception, and CPL would be 0. Okay, would be kernel mode. And why do we want to know the EIP? So this is, for a trap, the EIP is where we're returning to. That is, after the trap. This EIP is not after the instruction we're executing. This is the instruction pointer for the instruction we're executing, because we might want to try it again. How many times do we get to try it again? 2. Third time's the non-charm, right? Third time's the reset. That's what it is. So here's a trap frame. If you were looking up trap frames, you would find they're probably pretty similar between JOS and XV6. Always keep that in mind. So we've got the stuff that's pushed by the hardware. Okay? So this is what's pushed by the hardware. This X should be a W for hardware. So we've got the error. As you're looking at traps and exceptions, you'll find that some particular exceptions push an error and some don't push an error. Okay? For uniformity, we pretend it always pushes an error. And if we were in an exception that didn't push an error, we'll just put a 0 there. The instruction pointer, the code segment, error flags, these only get pushed when you're switching from user mode to kernel mode. Okay, so if you were in kernel mode and going to kernel mode, these wouldn't be present.
What's the padding for?
The padding is that this is a 16-byte value,
Yeah.
and there's 16 more bytes on the stack that we don't care about, because every one of these 32-bit values is at a 32-bit alignment, boundary. Very common, very, very common, if you are dealing with hardware, that you have to create a struct in C that matches what's in the hardware. And you have to be careful, because if you're not aware, the compiler has padding that it will do automatically. And it's usually better to make that explicit as to what the padding is. Okay. What type of fault is this? We're going to start doing this. So this is all in software. The hardware pushes this, goes into our vector, and we're going to now deal with it. The trap number tells us what kind of thing. We have other registers we store, more registers, more registers, more registers, more registers. Okay? So we've got this interrupt descriptor table that's an array of function handlers. One for every different kind of an exception. One kind of exception we've already seen is a trap. Another kind is now going to be a page fault. And for every one of them, the hardware pushes all this stuff. The hardware may or may not push error codes, depending on which exception it is. Where would you find the information of which pushes error codes and which doesn't? Say again. This is an architecture question of the x86, so where do you go to find answers about x86 architecture? The x86, yeah, architecture manual. That'd be a good place from Intel or AMD. Or go look in the XV6 code or the JOS code if you're working on one of the others. But the correct place to go is the x86 architecture, and it's very straightforward. It just says whether it has errors or not and what those are. So we've got this vector, this table or array of entries. So vector 1, vector 2, vector 3, vector 11, vector 12, vector 14, vector 15, all of these. And so if we get a page fault exception, it is going to go into here. And we then push 14 and jump to all traps. In all cases, we go to our single routine that handles all traps. Okay? And we're going to just push what was the exception. This is actually generated by a script. All right, so we're in all traps. So we got our hardware exception. We went to through our IDT, our interrupt descriptor table, and now we're in all traps, still written in C. Right? So what's on the stack right now? Like right here, as we enter all traps, what's on the stack? Gabriel. Is Gabriel here? Ashley. So the trap, that's a good point. The trap number is there on the top of the stack because that just got pushed from here. And then this is a jump, so we don't have a return here. So we got the trap number, and then what's below that on the stack. The instruction that caused it, along with some other stuff. Come on, scroll. Along with this stuff. So this is the stuff that is pushed by the hardware. So that's already on the stack. We push the trap number, and now our software needs to put the rest of the stuff. Okay? So our software is going to push all the rest of the things. So push DS, ES, FS, GS, push a bunch of registers. So this is a single call that pushes a set of registers. We set up a little segmentation, and then we push the stack pointer? What? Anyone? I'll give you a hint. Let's go look at trap. Trap takes what as a parameter? Trap frame pointer. And where is this argument passed? Where are all arguments passed? In C. On the stack. So we have to have a pointer to a trap frame on the stack. Where's the trap frame now? On the stack. We want a pointer to it on the stack. So therefore, we'll just push the stack pointer because that will be a pointer. Okay? When we're done, by the way, with a trap, we'll return from here and we'll undo everything. Pop, 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 pop. Add to the stack pointer to get rid of these things, and then do an interrupt return that undoes what happened when we came in. So we want to find out what virtual address caused the fault. So we can get that from the CR2 register. So the CR2 register holds the virtual address that last caused the fault. So there is an RCR2 C routine that will do that right in XV6. We want to know what else happened. So error contains some flags, like protection violation, right? So that's protection violation, yes. Okay, protection violation, trying to access something that doesn't have a U bit set. We're trying to write and it's not writable. Or we have a page fault and we were in user mode, as opposed to a page fault in kernel mode, which if we're in kernel mode, what do we want to do if we get a page fault in kernel mode? What can we do? Not much. We don't know what, I mean, something's terribly wrong and we don't know what. So the best thing to do would just be fail early. Panic with an error message like kernel page fault. Okay. Where it happened, so the instruction pointer. The code segment, we look at the bottom 2 bits and that'll tell us what mode we're in. Or you can look at this too. So either one of this will tell us what mode we're in. Katie?
The type of violation that the error with the 5 bits, are those flags like mutually exclusive? Like, is it only, it's either
I don't know. I don't know.
Okay.
Well, actually, the U is not exclusive, because we could certainly have the U with a write or without a write. But I don't know about the others. So for sysbreak, right, basically what we're doing is we got this. So this is how we made our way into sbreak, is by that same mechanism, right? The same mechanism that causes a page fault is the same mechanism, roughly, that causes a system call. Int for interrupt. What is it, 40, I think is what we're using for system calls. And so it'll cause the same machinery to eventually get us into sbreak, where we used to, how many people are not familiar with this #if? All right, so this is a good way if you want to comment out code to comment out code, and it's also a good way to show, right? Don't submit it like this, but for me to show the old code and the new code, it's a good way. So this was the old code, and the new code just says basically increase the size, the address space allocated to this process. GrowProc says increase the size and allocate physical pages for every one of those. And this one says don't bother. Just take their reservation, take their money, and give them a ticket with their seat number on it. But don't worry about any planes. Okay? And then the user program says, this is fabulous, I have this memory. Oh, what if I try to use it? Oh, you get a page fault. Except the user program never sees the page fault, right? Because it goes to the kernel. We get a kernel page fault. And we look, what trap was it? Oh, it's a page fault. We will look at the address that caused the page fault, right? And we will round it down to a page boundary, because it could have been any offset within there. And then we'll look and we'll see I just realized something funny about this. Yes. So we might have wanted, well, I'm just wondering about the page size. So dealing in page size increments, whether we possibly have a bug in this code. That is, I'm not 100% sure we want to round down here. I think maybe we don't. In any case, this check is saying, are we within, all right, that is, do I have a ticket? Is this address within the size that has already been allocated me? Or am I trying to write outside of it? Okay. If I'm trying to write outside of it, it's a violation. And we should do something here. Okay? Exit the process. Otherwise, let's allocate a page of memory. We allocate a page of memory. If we can't do it, uh-oh, we're out of memory. Sorry, this is the example of you're overbooked, right? So we will exit you, lucky you, and just return from here. Otherwise, fill it with zeros. Why is it important to fill with zeros? Sarah.
I mean, the page could have been used for anything before, so if you don't fill it with zeros, like a malicious person could try to read it and try to reconstruct
Yeah,
data.
it might have been used by my password program a second ago, and now I'm reading it in and it has passwords in there or something. So, yep, that's why we guarantee it's 0. And then we map the pages. So we say, this process's page directory at this address, which we do know is at a page boundary, one page, the physical location of this is, right, mem is a kernel virtual address. And so we want to convert that to a physical address. And let's let the user write it and read it.
So I've noticed
Yeah, right.
that when we're dealing with these addresses, sometimes they're void stars and sometimes they're char stars and sometimes they're just uints. And is there any? I just feel kind of uncomfortable when I'm picking what data I use.
Yeah, so I would suggest void stars is your best possibility. So this is for kernel virtual addresses. For physical addresses, never a pointer. Because if you declare something as a pointer, you're tempted to try and read or write from it. And you can't dereference a physical address. You can only dereference virtual addresses. So I agree with it. So sometimes they're integers to do arithmetic on. So the physical address will always be an int. And for JOS, I suggest that you use a phys_adder_t. It's just a type def for an int, 32-bit unsigned int, but at least that declaration tells you this is a physical address. Make sense? All right, so let's look at another optimization. So we looked at this S-break optimization, which is you do have this problem if you run out of memory, right? If you oversubscribe memory. So let's say you S-break some memory. You S-break a gigabyte of memory. Conceptually, it all comes back as zeros, right? And let's say you never wrote to it. If you never wrote to the memory, what's the difference between this page of zeros and this page of zeros and this page of zeros? Not much. As long as you read from them, you get zeros. It doesn't matter whether they're the same physical page or different physical pages. In fact, let's make it even simpler. Let's talk about read-only 0 pages. So if you've got, and let's say your address space, and within your address space you had some 0 pages that were read-only. Okay, now why we have them, I'm not sure. But they're 0 pages and they're read-only. So this is our virtual address space. Our physical address space, how many 0 pages do we actually need? Just 1. Because every one of these, right, so this is zeros, can map to here, and when they read, they get zeros. So that's basically what we're looking at doing here. Except they're, yeah.
No,
Dave.
I don't know, maybe we can cover this, but what if then you're starting to write like into pages?
Okay, so yeah, if you want to write into it, that becomes more complicated. So if we knew they were read-only, that'd be simpler. So the idea is, when you S-break, let's look at an example here. Here's our address space. And we've got some stuff. And then we've got some read-only ones that are mapping to the same zeros page. And some other stuff that presumably is this one. So from the point of view of the processor, we're going to make this be read-only. That is, we're not going to set the write bit. But from the point of view of the user, they want to be able to write to these. But until they write to them, let's just do this way. Okay? So if you S-break a bunch of memory, right, you can S-break. There are global variables is another way you could have zero-filled stuff. Right? Remember I talked about in C, when you allocate global variables, by default they're zeros. So there's an area of your memory when your process gets loaded, when your process gets executed, where we are allocating a chunk of memory that is all zeros for your globals. We can use the same idea here too. And we're going to copy the 0 page on write. So the idea is, if we try and write to this page, we'll go ahead and copy it to a new page and make it writable. So we'll leave the read-only one alone and make this one writable. So that's the idea. David?
Is there a flag that indicates that zero only? Is you wouldn't want to
Nope. So I'll show you how it would work. Let me clear my... You know what? We are over time. Do you guys... This is all we have to look at. So let's try and just look at this. And I'm sorry for taking you over time. So we get a page fault. We can tell whether it's a write or a read page fault. Okay? Let's say it's just a read. Okay? So just like this S-break case before. So we checked to make sure it's within our S-break area. And we're going to then map in a page. This is a 0 page we've allocated previously somewhere. So a page of all zeros. And we're going to reuse the same 0 page over and over again every time this happens. And we're going to just say user mode, but not writable. So that takes care of the first case where they try and read from this S-break area. We're going to give them back, instead of a brand new page, this 1 0-filled page that they can't write to. Now, if they try to write to it, we'll get a page fault. We come in here, it's writable, and we will look and we will allocate a page for it. A real page, because they want to write. And we'll set it to zeros. And we'll map it, writable. This may be remapping, right? So we might have done this map first, because we read from a page, And then when we write to the page, we're going to have to come in and remap that same address to a new page with new permissions that allows us to write. Questions on this before we go? All right, so I will be down in the cafe for another 35 or 40 minutes. Lab 2 is due tomorrow. You don't want to know about Lab 3, but it's out.